Now that we have a definition and an understanding of work, we can use that definition and that formula to derive new equations that can help us define different kinds of energy. And we're going to focus first on the idea of gravitational potential energy. And that word potential, remember, just means that it has the potential to put some object into motion. So it's kind of like a stored up available energy. And it's caused by gravity in this case, gravitational potential energy. In order to come up with a formula for it, we can actually, as I said, start with our concept of work. And let's imagine a specific situation where we're trying to lift an object up at a nice steady speed. So we're lifting something up, working against the force of gravity, and we're trying to lift it up at a nice steady speed. Well, let's look at what happens when we start with our work formula. So we start with the idea that work is force dot product with displacement. But in this case, remember, work is just some change in energy. And the change in energy is all in the form of gravitational energy. So the change in energy is going to be the amount of GPE gained by the object that we're lifting. And so we can say that even though we're looking for work, we're looking for some change in energy, that change in energy that we find is going to be the full amount of gravitational potential energy. And so we're going to use a new variable to represent it. We're going to use E for energy with the subscript G for gravitational. So it's E with a little g. And that's going to represent how much gravitational potential energy we have. And so really we can now make a new statement. And at this stage, we can say that Eg is equal to the force that we're applying multiplied by the displacement that it moves through. But again, if we're lifting something up against the force of gravity, and we're lifting it at a nice constant speed, then that means the force that we're applying must be equal to mg. It must be equal to the force of gravity that's trying to pull the object down. That's what it means to raise something up at a constant speed. Your upward force is balancing out the downward force of gravity. So now instead of F, we can actually say that this F can be replaced with mg. And that's what we do in our next step. We replace the F with the mg. And you notice that we also got rid of the dot, because the dot is about multiplying vectors that are in the same direction. It's to ensure that we always do that. But in this case, if we're lifting with an upwards force and the thing is moving upwards, then both force and displacement are in the exact same direction, and it becomes a straight multiplication. So really we've got m times g for the gravitational force part, and then that's just being multiplied by one extra piece, by the displacement. But when we're actually lifting something upwards, typically we don't talk about the displacement that it has, we talk about what height it reaches. And so we just now replace that with h for height. So that now instead of just talking about displacement, we can talk specifically about what height something has been raised to. And so we end up with a final form that says Eg is equal to mgh. So our gravitational force, or our gravitational potential energy can be summarized as mass times 9.8, that special acceleration due to gravity, and then multiplied by the height of the object. And from here on out, we can just use this final summarized formula. You're not always going to have to derive it from scratch, but this is just to prove to you and show that it's really just a derivation or an extension of what we already know about the work equation. But now we can arrive at our summarized formula where we have Eg equals mgh. So remember, Eg is energy, so we'll measure it in joules. M is just mass, which needs to be in kilograms. G is our same old acceleration due to gravity, so approximately 9.8 here on Earth, and it's in meters per second squared, or newtons per kilogram. And height, we'll just make sure that we measure in meters. And it's going to be above a certain reference point, typically the ground or the floor. And so it's the height that the thing is able to fall to. And so if there's something that's going to stop it from falling, like the ground or the floor or a table, that becomes sort of the zero level. And we just measure how much height something has above that reference level. So we can look at the unit analysis just to make sure everything makes sense. We know in the end that on one side of the equation we're getting an amount of energy. So whatever we get on the other side, we should get joules. So let's analyze what we have on the right side of our equation. Well, mass, we said, must be in kilograms. We then multiply by g, which has units of meters per second squared. It's an acceleration. And then we multiply by height, which we said we're going to keep in meters. If we take all of that and multiply it together into one big giant unit, it's a kilogram times a meter squared per second squared. And that is just a joule. So we've arrived at joules in a very different way than we arrived at it when we did force times displacement, but we still are arriving at the exact same unit. And so even though the fact that mgh looks like a very different formula than F dot d, or F multiplied by displacement, we still arrive at the exact same unit. We're still calculating an amount of energy in joules. So really what this means is we're getting some idea of how much ability to do damage a certain object has. That's what this potential energy really means. It's the stored up ability to do work on other things, to put something into motion. And so we can see why it's going to depend both on the mass of the object and the height. Something that has a greater mass will create a greater ability to do damage. It can do more work on the things around it, like dropping a watermelon versus dropping an egg. But we also know that the height is going to make a big difference as well. We can do more work and have a greater effect if we drop something from a higher height than if we drop it from a lower height. And so that's why it's dependent on both of those things. But of course, it also ends up depending on g, because it depends on how strongly gravity is going to pull things down, which on a different planet, or even on a different part of Earth, or at a different altitude above Earth, might be slightly different. But we'll just use simple Earth problems where we'll use the approximation of 9.8. And now that we're armed with a formula to work with, we can go directly to some problem solving and see what kinds of energy are involved. And so Galileo, for example, was famous for doing lots of experiments on falling bodies. So he took lots of objects and liked to drop them from high heights and analyze through very clever experiments how they compared to one another. So let's say he's doing an experiment where he drops a 1.5 kilogram watermelon off a 10-meter high roof. You can decide whether or not you want to try this experiment at home. But for us, we're going to try and find the gravitational potential energy that the watermelon has when he's just raising it to that height. Again, it'll be able to do some work on other things when it's dropped, but we're just trying to find how much stored up energy is available for it to do work on other things around it. So as always, we're going to state givens and requireds. So we are told that the mass of our watermelon is 1.5 kilograms. We are told that the height that Galileo is at is 10 meters. We are also always knowing that g is 9.8, so we keep that in mind. Meters per second squared, of course. And we are looking for Eg. What is the gravitational potential energy? Well, in this case, we go directly to our formula, Eg equals mgh. We're solving for Eg anyway, so we can sub directly in 1.5 kilograms multiplied by 9.8 meters per second squared multiplied by 10 meters of height. When we do all that, well, we already talked about what happens with the units. The units all combine together to give us kilogram meter squared per second squared, or joules, in other words. But when we do the calculation, we get 147 joules, or approximately, because we'll round to a minimum of 2 significant digits, we'll say 150 joules of energy. And as always, then you would create a therefore statement that says, therefore, the gravitational potential energy of the watermelon at that height is 150 joules. That's how many joules of energy it has available that could then be transferred to other things if Galileo decided to drop it, for example. Of course, we also have to keep in mind that this formula can be useful in situations where we might already know something about the energy involved, but we're trying to find out some other variable. So in this case, let's say we know that a penny has a mass of 2.35 grams, and it's dropped from the observation deck of the CN Tower. This one I'm definitely going to tell you, please do not try on your own. But let's pretend that we did this, and we drop it from the observation deck. We know through other observations or other experiments that its GPE, its gravitational potential energy, is 10.3 joules. We want to know how high it was dropped from. So what really is the height of that observation deck that it's being dropped from? So we can always state our givens and requireds. In this case, we'll write down that the mass is 2.35 grams. But remember, our cardinal rule for this is that we cannot keep things in grams. We always want to make sure that we're converting to kilograms. And that's important because our final answer is going to be in joules. And we saw earlier that joules involves the units of kilograms and not just grams. So we divide this by 1,000, and we get 0.00235 kilograms. And I know that's a very small number, but it's still accurate in terms of its number of kilograms, and that's the version of the number that we want to use. We now know, in this case, Eg, and it's 10.3 joules. We can always mention that G itself is 9.8 meters per second squared, because you probably have an indication that that's going to come up and be useful. But in this case, it's actually H that we're looking for. What is the actual height that the penny was being dropped from? Always good to write down our starting formula. We know that Eg equals mgh. But in this case, as you've already seen, we are not trying to solve for Eg. So we need to go back and use some of our math skills to do a little bit of rearranging. If you do a little bit of rearranging, you should get that H, height on its own, is equal to Eg divided by m and g. So remember, we're trying to get the H all by itself, so we don't want to just divide both sides by m. We also want to divide both sides by g. So we can actually divide by both at the same time. And we see that if we just divide those, we get the height. Let's substitute in what we know. We've got 10.3 joules. That mass is 0.00235 kilograms multiplied by 9.8 meters per second squared. And when we divide all of that out, you get 447.24, and then it kind of goes on like that with some other decimals. But we are going to say that it's approximately 450 meters. And again, a final therefore statement would be expected on a test or an assignment, just to state that therefore the penny was dropped from a height of approximately 450 meters. So always just keep in mind that this formula can be used not only to find gravitational potential energy, but through all of its rearrangements could also be used to find mass of an object or height of an object if we ever needed to. And in fact, if this question had been on some new planet where we didn't even know the value of G, maybe it was something different than 9.8, we could also rearrange this formula to solve for G as well.